This unit focuses on looking at some example problems to wrap up our understanding of the stereochemistry of cyclohexane. This includes looking at both the cis-trans relationships, or the so-called different configurations of cyclohexane derivatives. It also includes problems that focus on looking at the relative energies of different chair conformations of a particular molecule. So let's get started at looking at these relationships and the stereochemistry dealing with cyclohexane derivatives. So what we're going to start by doing is assigning the relationship between each pair of structures listed below as one of the following. So this could be phrased as a potential multiple choice type question. We're going to look at the relationship between the two structures on the left and describe their relationship as being cis-trans stereoisomers, different conformers, and whenever you see the term conformer, being thinking that you could switch between the two by doing a ring flip, or are they different constitutional isomers? So a good idea as you're going through example problems throughout these units would be to hit the pause button, try to solve the problem yourself, and then hit play to go through the answer. So first off, let's take a look at the problem on the left here, and we'll go through the solution to it. So the first thing that I would suggest doing when you're looking at these types of problems is determine first and foremost that the two structures are not different constitutional isomers. A common mistake that people make is when they're hurrying through this, they don't even look for the possibility that they are different constitutional isomers. Instead, they just look at the stereochemistry aspects to start with. And if two molecules are different constitutional isomers, then stereoisomerism is a moot point. Different constitutional isomers cannot be stereoisomers of one another. They have to be one or the other. So different constitutional isomers mean that you don't even from there need to look at whether the molecules are cis-trans or different conformers or whatnot. They are different constitutional isomers. That is a thing in and of itself. Stereoisomers and conformers imply that two molecules have to have the same connectivity between atoms. If they don't, that means they are instead constitutional isomers. So let's take a look at the structures that we're going to start with. So we have 1-chloro-4-methyl cyclohexane. And the structure on the right, we need to first ask, is that the same constitutional isomer as a different constitutional isomer? So we can start to address this by looking at the structure on the left and numbering it. We can go number 1 is chlorine, going on the ring, number 2, 3, 4 is methyl. So we would describe this molecule as having branches at positions 1 and position 4. We could describe it as a 1,4 substituted cyclohexane. Let's take a look at the one on the right and make sure it also has branches coming off at carbon 1 and carbon 4. If the branches are coming off at different locations, then the two molecules are constitutional isomers rather than any of these types of conformers or stereoisomers. So branch at carbon number 1 is the chlorine, going around the ring in the shortest direction takes us to here. Carbon number 4 is the methyl group. So both of these molecules have branches at carbon 1 with a chlorine, carbon 4 with a methyl group. Therefore, they are not different constitutional isomers. They have to be the same constitutional isomer, and therefore we can narrow this down to them being related as cis-trans molecules or as different conformers. So let's next up ask ourselves whether the two molecules are cis-trans stereoisomers. So to be cis-trans stereoisomers, what that means is that if we look at, say, the structure on the left, and we assign whether the bonds both are up or both are down relative to the carbon atoms that they are on, we'll see that the relationship there, the up-down relationship, is the same as on the right. Either both are cis or both are trans. So let's classify the molecule on the left as cis or trans. The bond to the chlorine goes up, so I'm going to label that as up. The bond to the methyl goes down, so I'm going to label that as down. One goes up, one goes down. Therefore, we classify these two groups as being trans to one another. Let's go over to the structure on the right. The group that is our methyl group is up relative to the carbon it's bonded on, so I'm going to label it as up. At carbon number 1, the chlorine atom is up relative to the carbon it's bonded to, so I'm going to label that as up. Both of those are up. Therefore, we would describe this molecule as being cis. Hence, we can describe the relationship between these two structures as being cis-trans stereoisomers is the correct response for this. Whenever you find that the two structures are set up so that one is cis and one is trans, you can automatically eliminate conformers, because conformers means if two molecules are different conformers, that means that they are just rotated around carbon-carbon bonds and they'll still both be cis or both be trans. If one molecule is trans and one is cis, automatically the category that this is going to go into is our cis-trans stereoisomers. So let's look at our next example problem here. And we're going to go through the same flowchart of first and foremost establish that these two are not constitutional isomers, and then from there tease apart whether they are cis-trans molecules or different conformers of each other. So first off, coming up with the numbering of each of these molecules, I'm going to go ahead and number our ethyl group as position number 1. We're going to take our shortest distance around the ring to come up with what the branch is next. So shortest distance around this ring on the left is going to actually go counterclockwise. So we're going to go 1, 2, 3. So we describe this molecule as being a 1,3 substituted molecule. We come to the one on the right, and we again start with our ethyl group at carbon number 1. And then we take our shortest path around the ring, like we would for IUPAC naming, to come up with our next group. And in fact, in this one, it doesn't matter which direction you go, so I'm going to go the conventional way of clockwise. So you go 1, 2, 3, 4. This is branched at carbon 1 and carbon 4, whereas the structure on the left had substituents at carbon 1 and carbon 3. So therefore, these two structures are related to one another as constitutional isomers. And from there, there's no point in looking at anything related to cis-trans or the conformer issue because constitutional isomers are in a category of their own. So we're going to be looking at these as constitutional isomers. At this point, you should be able to take any two molecules that you could look at and assign the relationship between them as falling into one of these three categories. And it will always be that just one of these selections is true. It can never be that two of those is true. If two of them are true, you need to go back and reevaluate exactly what's going on in the molecule. So with that, let's take a look at another example problem type dealing with cyclohexane conformations. We're asked here to draw the lowest energy conformer that is possible for 1-methyl-4-neopentyl cyclohexane. We're then going to assign whether that conformer that we've drawn would be described as a cis or a trans stereoisomer. And we're going to ask whether the ring-flipped conformer of this molecule is cis or whether the ring-flipped molecule is trans. So let's go ahead and first off draw the lowest energy conformer that's possible, period, for 1-methyl-4-neopentyl cyclohexane. So it's not specifying here in the problem whether the molecule that we're drawing has to be cis or has to be trans. It could be either. We're trying to ask absolutely, positively, what is the lowest energy structure that we could make for 1-methyl-4-neopentyl cyclohexane. So lowest energy structure has to be a chair conformation of some sort. So I'm going to go ahead and draw a general chair template here. And you could have also drawn the chair template that kind of leans to the left. I'm drawing the one that looks like it leans to the right is how I would describe it. At position 1, we're going to put a methyl group. At position 4, we're going to put a neopentyl group. And in order for this to be the lowest energy conformer that's possible, we want to put both of those bulky groups in the equatorial position to make the lowest energy that is plausible, period. So at position 1, we're going to put a methyl group equatorial. So I'm going to draw in my equatorial methyl group. And if you're having trouble drawing these chair conformations, it'd be a great time to go back and review the tutorial video on drawing chair conformations. So 1-methyl and then going around the ring. This was position 1, 2, 3, 4. And at position 4, we want to put in our neopentyl group. This would be a good time to remind yourself of what those alkyl group names are because you are certainly expected to know those. So we come over here, and equatorial is where we're going to put this group. It's a neopentyl group. So a neopentyl group has 5 carbon atoms in total, and it has a tert-butyl group as the next to the last carbon of the chain, like so. A tert group as the next to the last carbon of the chain, I should say. Tertiary carbon. So we have a total of 5 carbon atoms in here in this neopentyl group. So 1, 2, 3, 4, 5, and we're on the right track with drawing a neopentyl there. Since this is our lowest energy conformer, period, that's possible for any structure of 1-methyl-4-neopentyl cyclohexane, we have arrived at this, and we know we've arrived at this because both of these bulky groups are equatorial. Now we're asked, based on the structure that we've drawn, is this molecule best described as cis or best described as trans? So to answer that question, we look at the carbon atom that each group is bonded to. So I'm highlighting that in green at carbon 1. And we ask, is the group that's bonded there oriented below or above the carbon atom? This one is below, so I'm going to put it as down, meaning below. Over here, We look at position 4 and we ask ourselves, is the branch right to here, above or below? In other words, is it up or it's down? It's up. And so we would describe this as being the trans stereoisomer. So we could say, based on this information, due to the fact that the lowest energy conformer that's possible for this molecule happens to be a trans stereoisomer, that the trans stereoisomer of the molecule is more stable than the cis. So we've assigned this molecule as trans. And then we ask whether the ring-flipped conformer of this molecule is cis or trans. One way to solve this would be to draw out the ring-flipped version of this molecule. But if you remember your definitions of what we mean when we're talking about ring-flipped conformers, one of the things was that when we do a ring flip, cis will stay cis, trans will stay trans. The only thing that's changing in doing a ring flip is axial is becoming equatorial, equatorial is becoming axial, but the overall relationship in terms of what face of the molecule one group is on relative to the other stays the same. So groups that are on opposite faces to start with will still be on opposite faces at the end of the ring flip, and therefore the ring flipped conformer of the structure we've shown here is still going to be trans. So that goes ahead and wraps up this particular problem. We'll go on to the next problem here to wrap things up, and we're asked to draw the two chair conformers of trans, one isopropyl, two propyl cyclohexane. Which of these two is lower in energy? So in this problem, we're restricted a little bit more than in the last problem. The last problem didn't specify to start with what the stereochemistry was of the molecule we were dealing with. It left that open and just said draw whatever the lowest energy form of this molecule is, period. Here we're restricted to just the trans configurational isomer. So we're going to go ahead and try to draw the lowest energy structure of trans, one isopropyl, two propyl cyclohexane, and then we will go in and make the ring flipped additional chair conformation of that molecule. And again, as I mentioned before, it would be a great idea as you're going through these to hit pause frequently, draw out or go through the problem as much as you can until you get stuck or until you think you've reached the solution, and then hit play to check your work. It's really only through repetitive problem solving and forcing yourself to struggle through this stuff that you really get it down. You can watch me ride my bicycle many, many times, but it's not until you get on the bicycle yourself that you learn how easy or difficult these different problems are and really get the hang of it. So practice, practice, practice. All right, so we're going to draw the two chair conformers of this molecule. So I'm going to go ahead and draw one of those chair conformers. I'm just going to draw my template in here. So just some practice at drawing the chair template. And one isopropyl, two propyl cyclohexane, and we have to make that trans. So what I'm going to do is I'm going to start here by putting the bulkiest group, period, in an equatorial position for starters, and we're comparing an isopropyl group to a propyl group. Isopropyl is going to be more bulky than a propyl group. The reason is, even though those have the same number of carbon atoms, if they have the same number of carbons, the one that is more branched is going to occupy more space. You could illustrate this for yourself if you draw out or build a molecular model of an isopropyl group versus a propyl group. So the isopropyl group is going to be bulkier, so I'm going to put that anchored in the equatorial position to start with, so that I'll know I've created the lowest energy conformer of this molecule, because the lowest energy conformer by definition will always have the bulkiest group in the equatorial positions. I've plugged that isopropyl group in equatorial at position number 1 of the ring. Now what I need to do at position number 2 of the ring is plug in my 2 propyl group. And the location of the 2 propyl group, meaning whether it is axial or equatorial, in other words, whether it's pointed up relative to the carbon or down, is going to be determined by the fact that we've described this molecule as trans. So our first group, our isopropyl group, we put oriented downward relative to the carbon that it was bonded to. And so therefore, for the molecule to be trans, our group at carbon number 2 needs to be oriented upward relative to the carbon that it's bonded to make the molecule trans. So I'm going to show that angled upward. And then I'm going to put my straight up 3 carbon chain, CH2, 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 CH3 rather, there. And that's going to give us the trans 1 isopropyl, 2 propyl cyclohexane. We can recognize it as trans because at carbon number 1, the branch is oriented downward relative to that carbon. At carbon number 2, the branch that we're going to is oriented upward. Both of these groups would be described as equatorial, and certainly they are trans to one another. Now, for the next installment of this, we're going to draw the second of the 2 chair conformations, because that's what we're asked to do here, To draw the second of the two chair conformations of this trans molecule, we do a ring flip. That's by definition, conformers are related by ring flips when we're talking about these chair conformations. So we're going to do a ring flip, and I'll draw the ring flipped template in here, oriented this way. And by the way, it doesn't matter which of these two you drew first and second. I could have put this one that I'm drawing now on the left and the other one on the right. It doesn't matter. What does matter is where the groups are and that they are trans to one another, and we can pick out which one is lower in energy. Okay, so by convention, I'm going to put position number 1 right here, number clockwise around the ring. At position number 1, we placed our isopropyl group, so I'm going to go ahead and do that again. Since we've done a ring flip here, what that implies is that all of the equatorial groups become axial, all the axial groups become equatorial. So at position 1 to start with, we had our isopropyl group equatorial. Now it needs to become axial. So I'm going to put it oriented straight down. So I have CH and then 2 CH3 groups directly bonded to that carbon. So good, and that's axial down. At position 2, we had an equatorial group to start with there on the left. And now that needs to be an axial group. And at position 2 here in this version of the molecule, we need that to be oriented upward. And I'm putting it a little bit in bold to illustrate that it is in front of that ring carbon atom, carbon-carbon bond that's in back. So plug in our propyl group, CH2, CH2, CH3. And we should notice that once we've done the ring flip that the molecules that we've drawn, we started off as trans. A ring flip, as a consequence, will always stay. Whether it was cis to start with or trans, it's going to stay the same. So trans is still trans. We just switched the axial to equatorial and equatorial to axial. So of these two structures, definitely the one on the left is going to be the one that is lower in energy, because in this particular configuration of the molecule being trans, this molecule on the left actually puts both of those bulky groups equatorial, which is the best of all worlds here. So this is going to be definitely by far the lower in energy of the two structures. The one on the right by far is going to be the higher in energy, because that puts those two bulky groups axial. And when those groups are axial, they're going to be much closer in space with the other axial hydrogens that are on the same face of the molecule. And that's going to greatly increase the energy of the molecule, because the groups that are axial are all going to be too close in space, all the ones that are on the top face and all the ones that are on the bottom face. So we've in essence here drawn the lower energy molecule on the left, and certainly the higher energy molecule is there, the one on the right. So that concludes our segment for problem solving with cyclohexane derivatives and understanding the stereochemistry of cyclohexane. There are certainly additional problems in the Chapter 3 worksheets to help you get more comfortable and more confident and more competent with solving problems related to these cyclohexane structures.